Hi, everybody. Only two of you are there. Is there any exams going on today? I mean, in the coming week? Why is strength is so less?
Yes, sir.
Oh, exams are going on. Okay, coming week, like say tomorrow or something, you have any exams going on?
Sir, actually, one exam is already over, so it's
Oh.
for the whole month.
Okay. Fine. Yes, Trayan, good evening. We had vaccination today. Oh, okay. In your school, you had vaccination today. Strayan and Suprija, are you from same school? No, right? I don't think so. Are you?
Yes, sir. DAV Public School.
Oh, okay. You both are from same school. So you had vaccination today. Okay. Obviously, they will be feeling unwell. For two people, what do we do? Wait, let me call Raghav and ask him what to be done. Right. Okay. Okay, I think we'll continue. Okay, even though only two of you are there, maybe other people will be able to do the recordings. That's what this information I got. Right. Okay. So let me share my screen. We're doing thermodynamics, right? Yeah. So, okay, we were doing this enthalpies, right? So we'll just do a couple of questions so that you'll be able to, just revise whatever we have been seeing, right? And then move on to other types of enthalpies, right? Okay, right. So let us take some questions. Okay, so this thing is given to you. So first question is, so they have given this reaction, O3 gas giving O2 gas plus oxygen atom gas. Okay, right. So and the enthalpy value for this reaction is given to be 106.5 kilojoules per mole, right? 106.5 kilojoules per mole, and they have given the enthalpy of formation of O3, that is ozone, is given to be 142.7 kilojoules per mole. Right now, what we have to do is we have to find bond enthalpy, right, or say whatever, or bond enthalpy of OO double bond in O2. Right? Basically, you can call it as bond. This is because there's only one type of bond in this molecule. So either you call it as bond enthalpy or you call it as bond dissociation enthalpy. Does not make much of a difference. Okay, right? Think about it, and you can do it. And I'm going to help you. I'll give you maybe 2-3 minutes time to think about it. Right. Right, this is what you need to find. Okay, did you get an idea how to do this? Right. So fine, maybe let us write the reaction for this. Okay, bond enthalpy of O2. How do we write the reaction? O2 giving 2O. Enthalpy of atomization, basically, isn't it? Right? O2 has to get converted into oxygen atoms, or you have to break the double bond. Right? Okay, so basically for this reaction only, we have to find your enthalpy. That is nothing but your bond enthalpy, isn't it? Right? So can I tell, like, say, this enthalpy of overall reaction, right? Can I talk in terms of maybe enthalpies of formation, right? So how do you do that? So can I write 2 into enthalpy of formation of oxygen atom, right? 2 into enthalpy of formation of oxygen atom minus what should come? Enthalpy of formation of O2, which is going to be 0. Is it not? Right? Enthalpy of formation of reaction for this reaction is going to be 2 into enthalpy of formation of oxygen atom, right? Minus 0. Why 0? Because it is O2. We know that elements in their standard states, elements in their free states, they will have your enthalpy value has to be 0. Isn't it? Right? So if that's the case, if I can find just this value somehow, right? If I can just find the enthalpy of formation of oxygen atom, right? And I'll be able to multiply it by 2 and I'll be able to find your bond enthalpy. This is nothing but your bond enthalpy. Is it not? Right? And for that only this data is given to us, right? So they have given the enthalpy of this reaction, right? And can I write this reaction, the enthalpy of reaction as again in terms of enthalpies of formation, right? So that would be enthalpy of formation of oxygen atom, right? Plus 0 because I have O2, right? Minus of enthalpy of formation of O3 gas, right? And this value we know, right? And this value we don't know, right? So that, okay, so this value is given to us also. This enthalpy of formation of O3 is given to us. So that would be 142.7 kilojoules, right? And this value we know, right? That is 106.5 kilojoules is equal to enthalpy of formation of oxygen gas minus, let me write this properly, right? We'll write minus, what is this? 142.7. That's it. So now we'll be able to calculate our enthalpy of formation. Now that enthalpy of formation is substituted here, right? And you'll be able to get the bond enthalpy, right? Okay. So like this, you'll be able to solve questions very, very easily, right? It looks pretty complex, but it is not. Okay. Like if at all you know what and all are the tweaks you can do with respect to your different enthalpies, you are set about this. All right. Okay. So I think this was a good refreshing, right? What are the concepts you're using? Maybe one more problem we'll do. Right? One more problem we can do. Right. So next question. Right. So standard enthalpies of formation of, okay, they have given delta HF of SF6 to be, okay, delta HF of SF6 to be minus 1100 kilojoules, okay, and enthalpy of formation of sulfur gas, right? Sulfur gas is 275 kilojoules, right? and enthalpy of formation of fluorine gas atom, right? This is sulfur atom, this is fluorine atom, and that is given as plus 80 kilojoules, basically plus or minus 80 kilojoules per mole, right? Now they want to know what is the bond dissociation enthalpy, right? Bond dissociation enthalpy of SF bond in SF6. Okay, think about it. Oh, now more people joined. Great, good. So this is very similar to the previous question, I would say, right? You can, if you write the reaction for this, right? You know, for all you write the bond enthalpy reaction for SF6, right? You know how to collect it, right? Right. Obviously, we have SF6, we have 6 SF bonds, right? We have 6 SF bonds, right? So I'll be able to write bond enthalpy as 6 into bond dissociation enthalpy, 6 into bond dissociation enthalpy of SF bonds. Is it not? Right? Right. And we'll be able to write this bond enthalpy. How do you write the equation for this? We write it as SF6 giving a sulfur atom plus 6 into fluorine atoms, 6 fluorine atoms. This is your bond enthalpy. This is how we write. Right. So I will also be able to connect your bond enthalpy with your enthalpies of formations and stuff, right? And that thing is given to you, right? So how can I write this bond enthalpy? In this case will be equal to enthalpy 6 into enthalpy of formation of sulfur atom plus 6 into enthalpy of formation of fluorine atom, right? Minus enthalpy of formation of SF6. Right, so all the values are given to us. Sulfur's value given, fluorine's value given, SF6 value is given. So I'll be able to calculate a bond enthalpy. Now, once you calculate the bond enthalpy, you will be able to calculate the bond dissociation enthalpy of SF bond to be equal to bond enthalpy of SF6 divided by 6. That's it. This will be able to calculate, right? And this is coming from here. You'll be able to calculate this. Okay, I hope that makes sense, right? Are you guys following? Is everything okay? Are you finding it difficult?
Yes, sir.
Okay, fine. I hope everything is fine, right? Okay, people, I think we can now move on to different other enthalpies, right? Okay, so the next enthalpy we can have is enthalpy of neutralization. Neutralization. Okay, right, fine. So again, this is going to be very, very simple, right? You can take it with the definition first. I'm going to give you the definition of enthalpy of neutralization. It's not that important, okay? All the other enthalpies which you have seen, enthalpies of formation, enthalpy of combustion, bond enthalpy, enthalpy of overall reaction, those things are going to be very important, right? These and whatever you're going to see after this are not going to be that important. Okay, anyways. So enthalpy of neutralization, it goes like this, right? It is the enthalpy change occurring. It is the enthalpy change occurring when 1 mole of an acid, reacts with when 1 mole of an acid reacts with a strong base, to form products. Obviously, the products we know, salt and water, right? So I'll repeat the enthalpy one more time, right? It is the enthalpy change occurring when 1 mole of an acid reacts with a strong base to form products. Very simple, right? So I think for the neutralization reaction, what is going to be the enthalpy change? That is what is called as enthalpy of neutralization, right? Now, people, see, look at this. So we say enthalpy of neutralization, Now, before we move on to this, what you have to understand is enthalpy of neutralization will define only for acids. Only for acids will not define it for bases. Okay, only for acids will be able to define this. Okay, right. So we understand, actually, I even forgot one important point, right? So people, whenever you find enthalpy value of a reaction, to be positive, right? That is, it is greater than 0. Right, that means we know sign conventions also of Q. This is nothing but heat, right? Enthalpies of any enthalpy is nothing but heat change, is it not? Right. So whenever we say that whenever we find that the enthalpy change is going to be greater than 0 for a particular reaction or for a particular process, right, that we can conclude that it is going to be an endothermic process, right? And we can conclude that it is going to be an endothermic process, because whenever we say Q is positive, right, we saw a sign convention for Q. What it says that whenever Q is absorbed, that is, whenever heat is absorbed or heat is added to the system, that Q value is positive, right? So now also we can understand, whenever we see that the enthalpy value is going to be greater than 0, that means heat is absorbed, and obviously that means that particular process is going to be an endothermic process. All right. And another case is where obviously it is going to be negative, that is less than 0, right? Now, when we say that obviously energy will be released, only then we can say that it is going to have a negative value. So that is going to be an exothermic process, right? 1 second, people, hold on just a moment. Okay, right. So yeah, so this is how we define, this is how we see whether the process is going to be endothermic process or an exothermic process. Okay, right. So now obviously any neutralization reaction, okay, right, will always be an exothermic reaction, right? You might have learned about this in your 10th class also, right? All neutralization reactions are actually going to be exothermic reaction, right? Lot of heat will be evolved during the reaction. Right. So whenever we have an acid, right, and that reacts with the base to form whatever be the product, salt and water, right? So for this, the enthalpy value, this enthalpy of reaction will always be negative, okay, because it is going to be exothermic process. Okay, right. Now, if at all we have one acid, right? Say we have acid 1, right, reacting with NaOH. Now, see, we have to take only strong bases. If you just look into the definition given for enthalpy of neutralization, I told that any acid reacting with a strong base, that is the definition, right? So we have to take only strong bases. Any base you can take, but in most of the cases we'll be taking only NaOH. Okay, right. Say now I have acid number 1 reacting with NaOH to form products, right? And say the enthalpy value is delta H1, whatever be the value in negative, right? Say we can even give some number. Okay, say this is some minus 50 kilojoules. Okay, right? I'm just giving you some random number, right? And there is another acid 2, right? And that is reacting with NaOH to form products, right? And then the enthalpy value, that is the enthalpy of neutralization. Then that is nothing but enthalpy, right? I mean, enthalpy of this reaction is nothing but enthalpy of neutralization, right? Okay, so that enthalpy value, I mean delta H2, we are finding out to be say minus 60 kilojoules per mole. Right now, depending on the magnitude, you forget about the signs. Like obviously, everything is going to be negative only, right? Depending on the magnitude of the enthalpy value, right, you will be actually able to tell which is a stronger acid, which is a weaker acid. That is also possible. Okay, which will be, we'll be able to tell which is going to be a stronger acid, which is going to be a weaker acid, right? So you can easily understand that the strength of the acid is actually directly proportional to the amount of heat released. During the neutralization reaction, because only a stronger acid will undergo more dissociation to react with NaOH, and more product formation means more and more heat will be avoided. That is easily understood, right? Okay, so we can conclude that if this is minus 50 and this is minus 60, we can conclude that the acid 2 is a stronger acid than acid 1, right? That you can conclude like this. Okay, right? Whenever we have two different values of two different acids, that is enthalpy of neutralizations, whichever is going to give me higher enthalpy value of neutralization, that is going to be a stronger acid. That will be able to tell, right? And whenever we have strong acids, right? Whenever we have strong acids like say HCl, H2SO4, HNO3. Okay, now these values, that is the enthalpy of neutralization of these values are constants. Okay, because almost all of them have similar kind of strengths, right? Almost all are strong acids only, right? So all these acids will have some constant value. Okay, so whenever we want to represent strong acids, like say I want to represent HCl or H2SO4 or HNO3, we will just represent them as H plus. That's it. Okay, we will just represent them as H plus, and we don't have to write the full formula of the particular acid. Okay, and this H plus will react with OH minus to form water. Right, this H plus will react with OH minus to form water, and the enthalpy value, that is the enthalpy of neutralization value for all these acids, whichever strong acids you have, this value is a constant, minus 53.7 kilojoules per mole. Right, this is a constant value which you have to remember. But 90% of times the problems will not be asked, right? But if it is asked, right, you have to remember this value. Okay, and whenever we have weak acids, right? See, remember again, I'm repeating, for all the acids, considering that they have similar strength, because all are strong acids only, the enthalpy of neutralization value is constant, minus 53.7. Right, so obviously all the other acids, whatever be the acids you have, all of them will have a value lesser than minus 53.7. I'm talking about the magnitude. Okay, it will not be 53, it will be less than 50, let's say 47, 46, like depending on strength of the acid. It will not be 53. Okay, so whenever we have weak acids, right, say for example, I have CH3COOH, right, or say I have HCN, any weak acid you can take for that matter, right? And whenever we want to represent the weak acid, we write the full formula of the acid. We don't write just H plus. Right, we don't write just H plus, we have to write the full formula. Say if I want to represent CH3COOH, that is say enthalpy of neutralization of CH3COOH, I want to represent in the form of reaction, right? See this one, what is the representation? This one is, say for example, enthalpy of neutralization of HCl. I just write H plus. Enthalpy of neutralization of H2SO4. Again, I write only H plus, right? Okay, so in this case, we have to represent the full formula of the particular weak acid. Okay, so that is going to react with say OH minus, right? So it is going to form say CH3CO minus, and obviously whatever is the counter anion, Na means Na will come here, right? And obviously side product is going to be H2O. And the enthalpy, say if I give some values, this value is some X, the enthalpy value for this reaction is nothing but some X value. This is how we represent your enthalpy of neutralizations. For strong acids, we just write H plus irrespective of whatever be the acid you're talking about. But for weak acids, we are going to represent the full formula of the acid, right? And one more thing what you have to remember is, for strong acids, the enthalpy utilization is a constant value, minus 53.7 kilojoules per mole. That is a constant value irrespective of whatever be the acid you're talking about. Okay, right? So that is all about your enthalpy of neutralization, right? Okay, so any questions anybody has for enthalpy of neutralization? Right, okay, fine. I hope you guys are following. Right, so next enthalpy we can see is enthalpy of solution. Okay, enthalpy of solution. Right, now this enthalpy is a combination of two other enthalpies. Okay, right, this enthalpy is actually a combination of two other enthalpies. right? So let us try to understand what is it. Okay, so and remember this enthalpy of solution, right? Enthalpy of solution is a combination, as I told you, is a combination of two other enthalpy values. One is lattice enthalpy. Okay, one is lattice enthalpy, right? And the other one is actually going to be the solvation enthalpy. Right, solvation, or if at all you're going to use the solvent as water, right? Solvation, if at all use the solvent as water, I can also call it as hydration enthalpy if you use the solvent as water, or in general, in any solvent, in general, we can call it as solvation, but mostly we'll be using this term only, hydration, because in most of the cases, we'll be seeing water as a solvent. Okay, so very important relationship. The enthalpy of solution is actually a combination of two other enthalpies, lattice enthalpy plus your solvation enthalpy, right? Now, why is it like this? First, we will try to understand. Okay, why is it that the enthalpy of solution is actually like this? Okay, so it is very simple to define the enthalpy of solution. Enthalpy of solution is basically an enthalpy is occurring when a solution is formed. Very simple, right? Whenever say you add some sugar into water, right? There is some amount of energy changes happening there, right? So that enthalpy change is what is called, that energy occurring in that particular process is what is called as enthalpy of solution. Enthalpy is occurring in the process of making a solution, right? Okay, now people, you will again study about this in depth in your 12th class, because we have a separate chapter called as solutions, right? But let me give you a brief introduction to this, right? See, you have say solute, right, and solvent, right, and those two has to be mixed and you will be forming a solution, right? Say now in your solute, before mixing, we are talking about maybe only solid solutes for now. Okay, we're talking only about solid solutes for now, right? Okay, now what you have to understand is, say in here I have, say I'm representing solute as A. Okay, I'm representing solute as A. So here we will have AA interactions, that is solute interactions will be there, right? And then say, let me call solvent as B, right? So in solvent, we'll have solvent interactions only. Is it not? We'll have only solvent interactions only, right? So say this is again BB interactions, there is nothing but solvent interactions, right? Okay, and in solution, right? In solution, obviously, we're going to have these two getting mixed, right? So here we'll have solute-solvent interactions, right? Here in this case, you're going to have solute-solvent interactions, is it not? So what and all you have to observe here is we have to somehow break your A interaction, because only then you'll be able to, make A getting attracted to B. Right? Same way, here we have to break your BB interaction. That is, you have to break your solvent interaction. We have to break solute interactions. That is one kind of energy change. Is it not? Breaking the bonds, not bonds, the intermolecular forces, right? Between two water molecules, between two NaCl molecules, something like that, right? So we have to break your solute interaction. Between one solute and another solute, you have to break the interaction. Between one solvent and another solvent, you have to break the interaction. That is one type of energy change which we'll be observing, right? And next, you have to understand is the A, that is the solute and solvent, has to come together and they have to have some attractive force with each other in a solution, right? So this is another energy process, right? Whenever we know, right, whenever some bond is broken, energy has to be supplied, right? And whenever a bond is made, energy will be released. We already know that. Again, I repeat, whenever energy change, whenever we go for bond breaking, we have to supply energy. Energy has to be given to this particular process, right? And whenever you want to make a bond, right? Whenever a bond is formed, that time energy will be released. Is it not? Right? So here you will have one kind of energy change or enthalpy change, whatever you call it. And for this, we'll have one kind of energy change, right? And these two are the ones which are mentioned here. Right? So lattice enthalpy basically talks about these the energy which is required to break these interactions. Okay, this A interactions you have to break, BB interactions you have to break, right? So that is actually like that's not the exact thing, but this has something to do with basically this breaking of interactions. Okay, and we know whenever a new interaction is getting formed, whenever a new bond is getting formed, obviously some kind of energy will be released. Right? And that energy is nothing but your solvation or hydration energy. Okay, right. So we will give you proper definitions for this, don't worry, but this is the overall process. right? This is your overall process, right? Lattice enthalpy talks about the energy changes occurring during the breaking of interactions, right? And solvation energy talks about the energies occurring when new interactions are made between your solution and solvent and solute, right? I hope that makes a lot of sense, right? Okay, let us now define your exact things. Like what do you mean by lattice enthalpy? What do you mean by solvation or hydration enthalpy? Will I understand now? Right now, we will not use the term solvation for now. We'll use only hydration because that is what is going to be there for most of the cases. Not for most of the cases, for all the cases which you're going to see. Right. Okay. So now we'll try to define what is lattice enthalpy. Okay. Right. Now, people. See, what you have to understand is this. What do you mean by lattice is the first thing you have to understand, right? What do you mean by lattice is what you have to understand. Lattice is nothing but the structure, right? See, for example, if I take NaCl, right? If I take NaCl will be forming like this, right? Say Na plus, Cl minus, Na plus, Cl minus, again Cl minus, Na plus, Cl minus, Na plus, Na plus, Cl minus, Na plus, Cl minus, and this is going to you're seeing only in 3D, right? But it means you're seeing only in 2D, but it can actually come in front of you, go back of the screen, right? It is going to be entire arrangement. Okay, so this entire arrangement is what is called as your lattice. Okay, lattice is nothing but the structure of the crystal, right? Structure of the crystal. We generally talk about lattice only for crystals, ionic solids, right? Whenever we say crystal, means it is generally going to be ionic solids, right? Generally, obviously, because only salts will form crystals, is it not? Ionic salts only form crystals, right? So what is the structure of the crystal, right? Is what do you mean by this lattice? Okay, right. Now, how do we define your enthalpy? I mean, lattice enthalpy. It's very simple, right? So it can be defined as okay, take down the definition, right? You can take down the definition for lattice enthalpy, right? It is the energy change occurring. I mean, it is the enthalpy change occurring. It is the enthalpy change occurring. Then it is the enthalpy change occurring when the crystal lattice is formed. As simple as that, right? It is the enthalpy change occurring when a crystal lattice is formed. Okay, crystal lattice is formed. What amount of the crystal lattice? Crystal structure is formed, right? So when you're going to make the structure, when you're going to make the entire lattice, obviously some amount of energy will be released or some amount of energy will be spent, depending on what kind of crystal you're talking about, right? That energy is occurring, and that energy is occurring is what is called as your lattice enthalpy. All right. Okay, so that is about the lattice enthalpy. Obviously, you have to understand, right? Whenever you want to, put this in water, what is going to happen? This place is entirely going to get filled with water now. So this Na plus will try to move away, Cl minus will try to move far away because the water molecule is entering between them, right? So basically, that is why you have to understand, right? Between Na plus and Cl minus, between another Na plus and Cl minus, they have to move far away from each other. That is why we are saying that some amount of energy has to be supplied to break the lattice, to break the structure, and that is the reason why we are taking the help of lattice enthalpy in your enthalpy of solution. All right. Okay. So that is about your lattice enthalpy. Understood? That is the enthalpy occurring when the crystal lattice is formed or when the crystal lattice is broken. Actually, you can take that also. Formed or I already say enthalpy change occurring when crystal lattice is formed or broken. Okay, you can take that back. Okay, you can include the point for broken also. Right? Okay, and then comes your enthalpy of hydration enthalpy. Right? Okay, now we'll try to define your hydration enthalpy. Okay, right. So in hydration enthalpy, how do we define this? Right. So let us try to get a proper definition first. Right. Take on people. It is the enthalpy change occurring. It is the enthalpy change occurring when it is the enthalpy change occurring when 1 mole of an anhydrous substance, when 1 mole of an anhydrous substance, when 1 mole of an anhydrous substance gets hydrated. Okay, I'll repeat this in one more time for you, right? So it is the enthalpy change occurring, right? It is the enthalpy change occurring when an anhydrous substance, right? When an anhydrous substance gets hydrated, right? Now it is very simple to understand, people. Look at this. Say, for example, if I want to say enthalpy of hydration of CuSO4, right? Enthalpy of hydration of CuSO4 is some X kilojoules per mole. Okay, enthalpy of hydration of CuSO4 is some X kilojoules per mole. Now we have to take your anhydrous CuSO4, right? You have to take anhydrous CuSO4 means, you know what do you mean by anhydrous? Anhydrous means no moisture, no water is there. Okay, right. So now we are going to make it hydrated. Means what? We are going to add water to this, say 5 molecules of water, because we know that the hydrated salt is having a formula of CuSO4.5H2O. So this is your anhydrous substance, right? This is your anhydrous substance that we are going to add water to that. Okay, and that is going to become hydrated, right? That is going to become hydrated. Is it not? Right? So in this process, for the particular process, whatever is the enthalpy change is nothing but your X kilojoules per mole. That is nothing but an enthalpy of hydration. Okay, right? So obviously, like we have the anhydrous salt with us, right? So for like once you put into this, once you put what once you add water to that, the ions will try to move far away from each other, right? And that is a lattice enthalpy, and then they will get hydrated, right? And then they will get hydrated. That is what you have in this case also. Hydrated means what? The anhydrous substance gets water molecule inside into this. Okay, that's what happens here, right? Okay, so that is about your lattice enthalpy and your hydration enthalpy. Okay, right? And the overall, the lattice enthalpy and the hydration enthalpy has to be summed up to find your overall enthalpy of the solution. Again, that is very, very important, right? I don't know why I'm not feeling so good. My throat is paining suddenly. I don't know why. What is wrong? But I think we'll see what we can do. Okay. So I think that is about your different types of enthalpies. Okay. We have seen, I think, so many types of enthalpies, right? And you have to spend some time on this so that you will be able to get a hold on this. Okay. So these are all the different values, mean different types of enthalpies we can have, right? So now actually we can go back to your entropy that we have been discussing. We started discussing about entropy, if you can remember, and we started in between, and then we went on to this different types of enthalpies, right? Okay. Right. Okay. Right. So we know entropy, we know how we defined entropy was. Entropy was nothing but a measure of disorderliness, right? Disorderliness, right? It is a measure of how chaotic, how disoriented that particular system is, right? That is what is called as entropy. And we said that we will be representing it by the letter capital S. Is it not? Right? We will be representing by the letter capital S, and we know that we will not be able to measure your absolute entropy, right? We will not be able to measure the S value directly, but what we'll be able to measure is your delta S, right? Change in entropy that we'll be able to measure, right? And I even gave you a formula for this Q reversible by T, right? So like we have to assume that the process is actually going to be reversible, okay, right? That is like mathematically, that's what we need to do. Right? And eventually, if you see, even though I'm going to have an irreversible process, don't worry much about what is this Q reversible and all. It is way beyond the scope of your 11th. Okay, so don't worry about it. What exactly do you mean by this reversible? Why are you taking this Q reversible only? Don't really worry about it. Okay, so basically the heat change occurring in that particular process. That is what we have to understand. And mostly we'll be using your enthalpy values. Is it not? Because we know that heat change in occurring in a chemical reaction, for example, if we take that heat change is nothing but what? Enthalpy of the reaction, right? So in most of the cases, we'll be taking the enthalpy values as the Q reversible values. Okay, right. So done. I think we have told another some points also. If at all we compare, say, solids, liquids, and gases, gases will have the maximum entropy. Then comes liquids, then comes solids. That we already know. Is it not? Right? Gases will have maximum entropy than liquids, than solids, because now we know that gas molecules are randomly moving here and there, but solid molecules are almost stationary. They're not going to move, right? So obviously your gas molecules are more disordered compared to solids or liquids, right? That's why they have maximum entropy, right? Okay, and then we went on to see the second law of thermodynamics, if you can remember. Right, so if you can remember the statement also, right, the direction of spontaneous change, right? We know what we mean by spontaneous also. I guess that day we saw all these, right? So direction of spontaneous change should be in such a way that the entropy of the universe is increasing, or the entropy of the universe, or the change in entropy of the universe is greater than zero. That's what you have to understand, right? So the direction of spontaneous change should be in such a way that the entropy of the universe is actually increasing. Okay, that means delta S universe should be greater than zero for a particular spontaneous change. And we know what we mean by a spontaneous change. Spontaneous change happens on its own. Right? Spontaneous change will happen on its own. We don't need to do anything for the reaction to happen, or say we don't have to do anything for the process to happen. We just have to just keep them in contact. For example, a chemical reaction, or say at that particular temperature, eventually that's what is going to happen, right? So what do you mean by spontaneous change? And or more energetically speaking, right? We do not have to spend energy for the particle process to happen. Right? We don't have to spend energy for the process to happen. It will automatically happen by itself. That is what is called as a spontaneous change. Right? And for those kind of spontaneous changes, for those kind of spontaneous processes, the delta S universe will have a value which will be greater than zero. Okay, which will be greater than zero. Okay, so now, right now, maybe we'll try to have a proper example and see how this works. Right now, what you have to understand is it is delta S universe, right? And if it is delta S universe, obviously we have to sum up your system's change in entropy plus your surroundings' change in entropy. Right? Okay, right. So now maybe we'll take a specific example, right? A specific example we will take. See, when I go for boiling of water, right? When I go for boiling of water, is it right? Okay, we'll check whether it's going to work or not. Okay, when I take boiling of water, this happens at what temperature? This happens at 100 degrees Celsius. Is it not? This happens at 100 degrees Celsius, or it is actually going to happen at 373 Kelvin. That's what it happens, right? And the spontaneous process, isn't it? Right? At 100 degrees Celsius, we're not doing anything. The temperature is reached, and that till the water boils up, till all the water boils up, that particular temperature will not change, right? So at 100 degrees Celsius, this boiling of water is indeed a spontaneous process, right? At 100 degrees Celsius, this boiling of water is indeed a spontaneous process. So now we will check whether the delta S universe for that particular process is becoming greater than zero or less than zero. Obviously, since it's a spontaneous process, it has to come out to be greater than zero, right? Okay, now people, let us calculate enthalpy of system now. Sorry, entropy of system now. What is the system here? Say I have a vessel in which I have some water molecule. This is your system, right? And it is boiling also, right? It is boiling also. Okay, right. So now what is the formula for delta S system now? Right, delta S system formula is the heat change. Remember the formula here. Right, it is the heat change occurring in that process divided by the temperature at which the process is happening. Right, the heat change occurring during the process divided by the temperature at which this process is happening, right? Okay, so we can easily understand that this value that a heat change occurring during this process at 100 degrees Celsius, whatever the heat change happening, is nothing but enthalpy of vaporization of water, right? That heat change is nothing but enthalpy of vaporization of water, is it not? Right? Divided by what temperature? 373 Kelvin. Okay, divided by 373 Kelvin. And I need to know this value. Can someone Google? I don't need to Google it. 1 second. Okay. I want to know what is enthalpy of vaporization of water. What is the water is how much? Enthalpy of fusion, enthalpy of vaporization. This is enthalpy. Okay, 40.67. Huh? Okay, right. We'll keep this. Okay, so that value is some 40.67 divided by, this is your enthalpy, kilojoules per mole. Okay, 40.67 kilojoules per mole, and your temperature is 373 degrees Celsius. Okay, right. Now please understand the temperature of water inside, that is 100 degrees Celsius, right? But the surrounding, right? The surrounding is at what temperature? Say this is a room temperature only. Basically, I can tell this is your surrounding, right? That area, whatever I'm marking, surrounding this, right? Whatever is outside the particular beaker, that is your surroundings, right? And surrounding is at what temperature? Surrounding is at room temperature, that is say 25 degrees Celsius. Is it not? The water is at 100 degrees Celsius, but whatever is outside, right? The surrounding is at normal room temperature. It is assumed that I'm doing it around a normal room at sea level, right? It is the room temperature 25 to 27 degrees Celsius we can have, right? So now if I have to calculate enthalpy, you have to calculate the entropy of surroundings, right? Now what you have to understand is this particular heat, right? This particular enthalpy of vaporization, where is it coming from? It is coming from surroundings. Is it not? Again, I repeat, right? This 40.67 kilojoules is getting added to the system, right? That is why we give a positive value, right? That is getting added to the system. But where is it coming from? It is coming from surrounding. The heat flow is happening from surrounding to system. I hope you get it, right? The heat flow is happening from surrounding to system. I hope you easily get it, right? So for system, this much amount of heat is added, and that is why we give a positive value, right? But what will happen to surroundings now? The surrounding is actually losing the heat. Is it not? Because from surrounding only it is going to the system. The same amount of heat, that is 40.67 kilojoules, would have been lost by the surroundings. Is there anybody who has a doubt in this? Right? 40.67 kilojoules is getting added to the system. Okay, fine. Right. But where is the heat coming from? The heat is actually coming from the surrounding only. So the same amount of heat, that is 40.67 kilojoules of heat, right, would have been lost by the surroundings. I hope you're getting the point. The amount of heat is getting added to water, so we give a positive value. The same amount of heat is actually getting lost by the surrounding, right? So in this case, we'll write minus enthalpy of vaporization of H2O divided by temperature of the surrounding. This in this case is 373. This is your temperature of the system, right? I have to take the temperature of surroundings. Okay, so that will be minus 40.67 kilojoules per mole divided by temperature of surroundings. We know is we'll keep it as maybe 27 degrees Celsius so that we'll be able to get a round figure, right? So if I keep it as 27 degrees Celsius, this thing is 300 Kelvin. No issues. Okay, this is nothing but 300 Kelvin, right? So now we got enthalpy of system, we got enthalpy of surrounding. sorry, not enthalpy, sorry, I'm so sorry, change in entropy of system, and we got change in entropy of surroundings also, right? Now we can calculate, right? Now we can calculate entropy of the universe will be equal to, that is nothing but entropy of the system plus entropy of the surroundings, right? So let us add these two values now. So we had 40 plus 40.67 divided by 373 for your this thing, right? For your what is this, for your system, right? Plus enthalpy of surrounding was minus 40.67 divided by the surroundings temperature is 25 degrees Celsius. So it was 300. Right now, if you calculate the value, are you getting a negative value or a positive value? Are we getting a positive value or a negative value? I think it's a positive value only, right? The denominator is,
yeah, sir, it'll be negative.
Okay. What mistake are we doing now? We took everything to be correct only. This is a spontaneous process. 100 degrees Celsius. It should be coming greater than 0, right? But it is coming less than 0. Some mistake we are doing. Okay, maybe if I take melting, what will happen? If I take melting, that will be whatever be the value, fusion will happen. That is at 0 degrees Celsius. This is at the same amount of heat will be lost. Okay. For melting, it is working, but for why for boiling it is not working? Okay, let me check this, people. Let me check this. I'm telling something wrong here, but it'll absolutely work for melting of ice. Okay, let us do this. Okay, this will keep on hold, right? You also check this, how exactly this is a spontaneous process, right? So let us do this. If I take a fusion, that is nothing but melting. Okay, that is nothing but melting. Right? So now what happens here? Basically, H2O in solid phase will go to H2O in liquid phase. Right? Okay. Now fusion, obviously, this happens at what degree? This happens at 0 degrees Celsius. Right? So obviously the system, right? System will be in 273 Kelvin, right? And the surrounding will be at room temperature. Surrounding will be at room temperature, that is going to be 300 Kelvin. That is nothing but 27 degrees Celsius. Right? System will be at 273 Kelvin and the surrounding temperature will be the room temperature. Right? Okay. So if that's the case, now if I calculate the entropy of the system, that would be enthalpy of fusion of H2O, whatever be the value, right? Divided by 273 Kelvin, right? And entropy of surroundings, right? That would be minus. Now again, same thing, right? This heat, whatever the heat which is gained by the system would have been lost by the surroundings, right? So minus enthalpy of fusion of water divided by the outside temperature is 300 degrees, 300 Kelvin. Right now, if you check the entropy of the universe, change in entropy of the universe, that will come out to be positive. Okay, that will come out to be positive. But I think I don't know what some kind of mistake we are doing in case of boiling. Let me correct that. Okay, I will look into this and let me correct that. But for fusion, you can easily understand. We know at 0 degrees Celsius, if you're going to maintain, easily the ice will melt. We are not doing anything. Right? We are literally not doing anything. The ice automatically melts. It's a spontaneous process, and you understand that for a spontaneous process, we are seeing that the delta S universe is going to become greater than 0. Okay, and for boiling, let me clarify what exactly is going to happen. What are we doing wrong there? It should also be greater than 0 only. When you calculate your delta S universe, right, you should be getting a value which is going to be greater than 0. No doubt about it. Okay, right. Fine. So that is about your second law of thermodynamics with respect to your spontaneous change. Okay, there are going to be so many statements, right? There are going to be at least one more statement will give you, right? There's going to be one more statement also which I'll give you, that is going to be with respect to engines. Okay, we'll see about engines also. You might study about engines in your physics also, right? But here will be little like just touching it, like little about that also we'll see, right? Okay. I don't know whether I want to continue the class because I am also not feeling well. How many people? How many people? We have four, I guess, right? No, we have 1, 2, 3, 4. 5 of you are there. Fine, I think we will actually continue. Like let us complete the portions also. Right, people. Like, okay, actually, we can go for the break. Right, we'll meet by 6:50. Right. Time is almost like 6 o'clock. We'll meet by 6:15. We'll meet again. I'll be completing this chapter today mostly, right? And right after we complete the chapter, I think we'll leave also. Okay, right. Fine. Let me switch off my video. Let me mute myself. I'll be back by 6:15. You also be back. Okay, sorry guys, I became a little late. I was eating something. So yeah. Okay, are you guys back? Shall we start? People?
Yes, sir.
Okay. Right. So yeah, we saw how this second law of thermodynamics works in case of fusion, and I'll tell you how it works in boiling also, but not today. Right. Okay. So we understood that any spontaneous thing, if it is going to happen, the delta is universe, for that it is going to be greater than 0. Right. Okay. Now there is another way of defining your second law of thermodynamics, not in terms of the spontaneous change, but in terms of engines. Right. So we will see second law. What is wrong? Pen. Right. So we will see there is something wrong with the pen. Okay. So we oh, something is wrong. Just a moment. Okay. Right. So now it's better, little better. Okay. So second law of thermodynamics with respect to engines. Okay, right. Now, generally, how engines work, if you ask me, right? Any engine, I'm talking about a thermo engine, right? How normal engines you use in your bikes, in your this thing, right? Everything will have almost similar kind of property, whatever I'm going to tell. This is a very basic thing, right? And obviously, you can add on so many features and all, you'll be able to make a good engine also, right? So, in any engine, right? In any engine, right, we are going to have something called as a heat source. Okay, we are going to have your heat source. Okay, now that heat source will be now given to your actual engine, right? That from the heat, basically some amount of heat from the heat source will be given to your engine. Okay, and obviously this particular engine will take up this heat, and it is going to give us work output, right? It is going to give us work. Okay, and during that process it will also have one thing, it will also have something called as a sink, right? This is a heat sink, both are heat source and heat sink. Okay, right. So this will again be giving say this is q1 amount of heat, right? Some amount of heat would have been lost to this particular sink also. Okay, right. Now you can ask me, sir, some heat is getting added, and that amount of heat is now getting converted into some amount of work done. But why is there a heat loss also happening? That is how second law, that is what second law says, right? So second law says whenever you do some work, right? Whenever you do some work, or whenever some amount of heat is getting converted into work, that amount of heat loss is inevitable. You cannot make this zero. Okay, you can never ever you can reduce it little, like you can reduce it to almost zero, but you cannot make this zero. Okay, so that is what is your second law saying. Basically, if I have to put the proper statement, you can take down, right? You can take down the proper statement with respect to engines, right? There can be no engine, there can be no engine, there can be no engine which will be able to convert, which will be able to convert, there can be no engine which will be able to convert all the heat given to it, all the heat given to it, all the heat given to it into 100% work, into 100% work. Right, I'll repeat the sentence one more time fully, right? So what it says is that there can be no engine, there can be no engine which can convert all the heat given to the engine into 100% work. It can never, there can be no engine like that, right? There will always be a heat loss to the surrounding like this, right? Say, for example, if this Q was 100 joules, right? The work output cannot be equal to 100 joules, right? It cannot be, right? Anyways, it cannot be equal to 100 joules. It will be maybe say 99 joules, 98 joules, 97 joules, but it cannot be 100 joules because some amount of this amount of heat will be going as heat loss to the sink. Okay, so this is how any engine for that will work, for that matter will work, right? No engine can convert all the heat given to it into corresponding work. 100 joules of heat means no, it's not like you're going to 100%, 100 joules of work. We'll always get say only 95 or 90 or something, 70% only sometimes. Normal, the engines which we have now, which are using in your bikes and all, they have only maybe some 70% efficiency, right? That means if you give 100 joules of heat, only 70% of work output will be able to get, rest 30% will go out heat loss only, right? That is the even now we are not nowhere close to go for 100% efficiency, nowhere close, right? Now there are certain things to remember about source. The source will be at very high temperature. The sink also should be at very high temperature. Okay, the source and the sink should be at very high temperatures. So this you have to remember once, right? And they both of them, right? Both of the heat source and the heat sink should have very high heat capacities. Right? Should have very high heat capacities in the sense that even though some amount of heat is lost and even though some amount of heat is gained by the sink, the temperature what was maintained. Say for example, if this temperature was T1 and this temperature was T2, there is some amount of heat lost by the source and there is some amount of heat gained by the sink, right? Even during the process, this T1 and T2 should not change, right? So even though some heat is getting added or even though some heat is getting lost, there should not be any change in temperature. Ideally, obviously, ideal situations, right? That is why we say that we should have high heat capacity. Why? Because we know, right? It is the heat energy required to raise the temperature of the particular substance by 1 degree Celsius or 1 Kelvin. So to increase the temperature by 1 Kelvin, how much heat is required is what is called as heat capacity. So I'm telling that the source and sink should have very high heat capacity so that little small amount of heat changes there and there is not going to change the temperature. As simple as that. Okay, so this is the framework. Okay, source will be there, some Q1 will be given, and out of that some work can be extracted, and obviously some heat loss will be there, and this heat loss can never be made equal to 0. Okay, right. Now there is a way by which you, okay, I'm going to contradict my own statement. Okay, now I'm going to contradict my own statement by saying that Q2 can be made equal to 0, right? Q2 can be made equal to 0. How, sir? How? Right? Now, if you can do the process 100% reversibly, right? If you can do the process 100% reversibly, right, you will be able to make this heat loss as 0, right? You will be able to make this heat loss as 0, right? And we know what do you mean by 100% reversibility. That means it is going to be infinitely slow. We know what we mean by reversible processes. Reversible processes are very slow processes, right? Now, if I say 100% reversible, means I have to reach from one point to another point, and I should reach only an infinite amount of time, right? Practically impossible again, right? But if you're able to do that, yes, you can make the heat loss to be going to 0. You can convert the entire amount of heat whatever you give into work. You can do that, no issues at all, right? But again, obviously you understand that practically it is not possible, right? Now there is another way also by which you'll be able to make this heat loss to be 0, right? If 0 Kelvin you can reach, if 0 Kelvin is reached, and in that particular temperature you do the process, right? The engine is doing its work at 0 Kelvin, right? 0 Kelvin is what? Minus 273 degrees Celsius, right? Now, if we can go to 0 Kelvin, and this is what is called as absolute 0, right? Guys, it's not my mistake that I'm writing like this. Okay, there's some problem with the stylus and the pen. Okay, please bear with it. Okay, right. So if this is not okay, right, you can write this 0 Kelvin. Okay, now this 0 Kelvin is nothing but minus 273 degrees Celsius. If the engine can do the process at 0 Kelvin, then I can make sure that the Q2 is 0, right? Then I can make sure that the Q2 and that the heat loss which is happening is going to become 0, right? And there is another statement, another form of statement of second law of thermodynamics saying that 0 Kelvin cannot be reached. Okay, So 0 Kelvin, again, there is another form of third law, sorry, second law of thermodynamics, which says that 0 Kelvin cannot be reached, right? In reality, also, we are seeing that we have not reached 0 Kelvin yet. We cannot go to that sub-zero, we cannot go to that particular temperature, minus 273 degrees Celsius. I think we have reached around some minus 250, something like that, right? And it is impossible. Like, so if at all you're going to reach your minus 270, that means you are actually, violating the nature. You are actually going against nature, something you're doing that. Oh, I think only if it is possible, maybe not on Earth. Okay, 0 degrees, 0 Kelvin is not possible. Maybe not on Earth, not on the universe, which we know, right? But maybe in some other universes, maybe it is possible, right? And this was all. See, the thing is, the laws of thermodynamics, okay, the laws of thermodynamics do not have consolidated proof. Okay, they do not have proof as such, right? But they are all made out of observations, right? All the first law of thermodynamics, second law of thermodynamics, third law, you don't have to worry about it, it's not there in your syllabus. But still, even if you third law of thermodynamics, you will see that these are mere natural observations scientists made and they gave it as a law, right? And there is no concrete proof, or like say, we'll not be able to prove it in a lab, or say we'll not be able to prove it during experiments, but that is what you observe in reality. That is how you see it. Okay, and that is how these laws are working. Okay, anyways, so again, very interesting, saying that this heat loss, whatever type of work you do, whenever you extract work from the engine, there will always be a heat loss. You can make the heat loss 0 if you do the process reversibly, 100% reversibly. Again, that is not practically possible. Or if you can reach 0 Kelvin and do the particular process, if you can reach, if you can make the engine work at 0 Kelvin, then again, you can go for this Q2 becoming 0. But again, that is not possible. I told you that is another form of second law. 0 Kelvin cannot be reached, right? Okay, so this is what you have to understand about second law of thermodynamics. Okay, right? So one is about the direction of spontaneous change, saying that the delta S universe value has to be greater than 0, right? And second thing is that this engine, with respect to this engine, it cannot go for having 100% efficiency. What is 100% efficiency? Whatever is the amount of heat given, getting converted into work, that is not possible. Okay, right? So people, one more thing is, we will be able to calculate the amount in efficiency, right? We will be able to calculate the efficiency of an engine. Efficiency of an engine, right? So how can we do that? It's very simple, right? Say again, I'll draw this thing. So we have the source, right? And now we have the engine, right? And then we have your sink, right? So from here to here, some Q1, from here to here, Q2, and here I'm going to get some work output. From the engine, I'll be able to make some work output. Basically, the engine running, the vehicle running, fan running, something, right? Some mechanical work output we'll be able to get, right? So we can say that the efficiency, right? The efficiency is denoted by efficiency, right? Is actually denoted by the letter. It is denoted by the Greek letter eta, right? This is how we write it. Okay, maybe I am already, the handwriting is bad and it is in my hands. So great. Okay, something like this. This is what is eta. The efficiency is a symbol. Okay, now that eta, basically more and more is the work output, more and more will be the efficiency for the given amount of heat. Say I give 100 joules, right? I'm able to get 99 joules of work output. That means the efficiency is 99%, right? Say I'm giving 100 joules of heat, right? But I'm able to get only 80 joules of work. That means my efficiency is only 80%, right? Like that we'll be able to calculate it. Okay, so it's very simple to understand, right? So this one is nothing but whatever the work output you are getting, right? Whatever the work output we are getting for the amount of heat given to us, right? That is the W by Q1 is nothing but your into 100 is what is your efficiency, right? Now you can also get this in terms of this thing, right? We know W is what? W is nothing but the difference between, say for example, if I say 100 joules of heat is coming here, 80 joules of heat is coming here, obviously Q2 would have been some 20 joules, is it not? Right? So so can I tell that W is also equal to Q1 minus Q2, right? Q1 minus Q2, right? So now we'll be able to write your efficiency as Q1 minus Q2 divided by Q1 into 100. right? That because I'm changing W to Q1 minus Q2, right? So now what can we write? This is equal to 1 minus Q2 divided by Q1, right? See, if they ask in terms of percentage, you multiply by 100. If they ask you in terms of fraction only, then you don't have to multiply by 100. Okay. Anyways, we multiplied by 100. You can also multiply by 100 in terms of, but whenever you tell the answer, you tell in terms of percentage. Okay, that you do, right? So 1 minus Q2 by Q1 into 100, or you can just write this is in terms of percentage, right? This is in terms of percentage. If you don't want percentage, you can just write eta is equal to 1 minus Q2 divided by Q1. That's it. That is also fine. That is your efficiency anyways. Okay, it is that is not in terms of percentage. Okay, right. Now we know that Q1 is related to T1, and that is temperature, and Q2 is related to temperature T2, right? So I can also give another formula. Eta will be equal to temperature 2 by temperature 1. T2 by T1. That is temperature of the sink, right? And temperature of the source. T2 and T1. Okay, where T2 is the source temperature. Sorry, that is actually T1, right? T1 is your T1 is your source temperature, and T2 is your sink temperature, right? And obviously the Q2 is the heat gained by the sink, right? And Q1 is the heat taken out from the source. Right? This is what I have to remember, right? And like this, you'll be able to calculate the efficiency. All right. Okay. Right. So obviously, what you have to understand, if this T2 can become 0 Kelvin, right? If this T2 can become 0 Kelvin, obviously the efficiency will be equal to 1 or 100%. Again, that is not going to be possible because this T2 you cannot make 0, right? So the sink temperature you cannot make 0, right? And also, if at all, you cannot make Q2 0 also, because if you can make Q2 to be 0, again, you will get the efficiency as 100%. Again, that is not going to be possible, right? So there cannot be any engine with 100% efficiency. No engine can do work like that. Okay, right? So that is about your engine efficiency. Second law with respect to engines, all those things we saw. Right now, coming to the last part of the chapter, we are going to complete the chapter and then we can wind up also. Right. So now, people, like say, I want to talk about. Why is it so dark? 1 second, let me switch on the light. Okay, so what I'm trying to say is, say I want to see whether a process is going to be spontaneous or not. Okay, I want to see whether a process is going to be spontaneous or not. So what should I do? Now I have to calculate the entropy of the system. Then I have to calculate the entropy of the surroundings, add them up, then check whether the entropy of the universe is going to be greater than 0. Then only we can tell that. It is going to be a spontaneous process. Right. So too much of work, isn't it? Too much of work in finding out whether particle process is going to be spontaneous or not, because you have to calculate for system, then surrounding, then universe, then see whether it is going to be greater than 0. Too much of work, right? So for these purposes, scientists gave another thermodynamic term. They introduced one more thermodynamic term, which is going to be used for deciding the spontaneity of a particular process. Okay, so scientists actually introduced one more thermodynamic term just for the sake of deciding your spontaneities. Okay, and that thermodynamic term is nothing but your Gibbs free energy. Okay, that is nothing but your Gibbs free energy. Okay, and it is denoted by the letter delta G. Again, it is absolute Gibbs free energy. Makes no sense, right? Change in Gibbs free energy, yes, you'll be able to delta G. You'll be able to measure. Okay, right. So the why did scientists come up with this new thermodynamic term? Right? Why did scientists come up with this new thermodynamic term? Is because just by measuring the delta G of the system only, right? Just by doing it to the system only, then we'll be able to tell, okay, that process is going to be spontaneous. That process is not going to be spontaneous. Like that, we'll be able to tell, right? If at all I'm going to use entropy, we have to calculate system entropy, surrounding entropy, add them up, and so much process. But if at all I'm going to use what is the Gibbs free energy for spontaneous processes, like say for deciding whether it's going to be spontaneous or not, we have to calculate change in Gibbs free energy only for the system, and that is enough. And I'll tell you how do we decide whether it's spontaneous or not, but that is the advantage. Okay, you do it only for the system, And that's completely all right. With that, you'll be able to tell, okay, that is going to be a spontaneous process or not. That will be able to tell with the help of this delta G. Okay, right. So now what is the definition of this mathematical definition? What scientists give? The mathematical definition, what scientists gave is G, that is Gibbs free energy, is equal to H minus Ts. Basically, this, right, delta G is equal, this G is the Gibbs free energy. This is your enthalpy, absolute enthalpy, but again, makes no sense. T is the temperature in Kelvin, right? And S is the absolute entropy, right? See, don't ask me how this is derived or how is it made. This is how scientists defined it. The definition itself is like that only. Okay, right. So now we can write it like this: delta G is equal to delta H minus T delta S. That is how you will be able to mathematically exactly define your Gibbs free energy, change in Gibbs free energy. Change in Gibbs free energy is equal to delta H minus T delta S. Okay, right. And okay, fine. We understood the mathematical definition. We understood what is the advantage of using this Gibbs free energy and all. But what exactly is the normal definition? Say in by words, if I have to define Gibbs free energy, how do I define it? Right. So this is how, like, I don't want to go into so much depth into this, whatever I'm going to say. But if you are interested, you can go further and read about it. Okay, right. So Gibbs free energy is the maximum useful work that can be extracted from a process. That can be extracted from a process. Okay, that is exactly how we define the Gibbs free energy. Okay, it is the maximum useful work that can be extracted from a process. What do you mean by maximum useful work? Okay, it has something to do with, again, reversible processes. Okay, right, it has something to do with reversible processes. I don't want to go into the details. If you are interested, please go ahead and read further about it. You will get more insight about it. But again, for your exam point of view, for your 11th, this is enough, right? Okay, so this is how we mathematically define this. This is how we properly give a definition to this. Okay, right. Now, what is the condition for spontaneity? Right, what is the condition for a spontaneous process, right, with respect to your delta G, right? So condition for spontaneity is that the delta G of the system should be less than 0, right? Delta G of the system should be less than 0. If it is negative, if I find that for a particular process the delta G value is negative, yes, I can say that it is going to be a spontaneous process. Very simple. And please understand, here delta G of the system only, here also the system, temperature of the system, and the delta S of the system only you can have to calculate. Okay, right? And these, for all the chemical reactions, the delta G value is already calculated and you have a table and all. So you are not using it all these things, but I'm telling you, you don't have to calculate anything. Everything is already known and they have been tabulated. Okay, so all that we have to understand is this is going to be part of this thing is going to be temperature dependent. Please understand. For example, certain reactions will not happen at room temperature, right? Because they are not spontaneous. They are not spontaneous at that temperature. But if you increase the temperature, those reactions will happen. Why? Because only at that temperature they become spontaneous. I hope that makes a lot of sense. Right? Certain reactions will not happen at room temperature, right? But if you increase the temperature, those reactions will happen. Why is it like this? Because the delta G of that particular reaction is going to become negative only above certain temperature for that particular process. At room temperature, delta G value is greater than 0, right? And that is the reason why you're seeing that the reaction is not happening at all, right? So for any reaction to happen, at any temperature, the delta G value should be less than 0. Only then the reaction will happen, right? Okay. So in your book, they might have given you different combinations. What will happen if delta H is positive, delta H is negative, delta S is positive, delta H is negative. Depending on the temperature only, everything is decided. Okay. So for example, say if this value is negative and this value is positive. Just telling you one example we'll take, right? Delta H value is negative and delta S value is positive, right? Now I want this overall thing to be negative. This is what I want, right? Right? So if at all this is negative and this is positive, right? So you can easily tell that this particular reaction is going to be spontaneous almost at all temperatures. This is not why, because we have a negative sign here. right? And this is going to become positive. So overall, this term is negative only, whatever be the temperature, because temperature cannot be negative, right? And this value is already negative. So in this particular case, if at all I have a process where the delta S is negative and delta S is positive, that particular process or reaction will be spontaneous almost at all temperatures. All temperatures, doesn't matter whatever the temperature is, it is going to be spontaneous, right? But say, let us take another case. I have delta G is equal to delta H, right? Delta G is equal to delta H minus T delta S. Say, for example, this value is positive, right? And say this value is negative. Okay, this value is positive and this value is negative, right? So what I have to understand now, now whatever be the temperature, I want this to be negative overall, only then the reaction is spontaneous, right? This value is positive, so I cannot do anything about it. Now negative into negative is going to become positive, right? So whatever be the temperature, this particular thing will be a non-spontaneous process, whatever be the temperature, right? Whatever be the temperature, like whether you increase or decrease or whatever you do, this entire term cannot become negative. That means this process cannot become spontaneous at all, right? Say another case we can take, right? Say we have delta G is equal to delta S, delta H minus T delta S. Say now I'm telling that this value is positive and this value is also positive, right? This value is positive, that is delta H is positive and delta S is also positive. Okay, now this is positive term. Now negative into positive, this term will be a negative term. Okay, so I want this term to be very, very, very high compared to this term. Only then this is okay, right? Only then the overall term will become negative. Again, I repeat, this is positive, right? And negative into positive will become negative again overall, right? But I want the overall thing to be negative. That means the T delta S value should be greater than delta H. Obviously, only then overall we can say that the overall delta G value will be negative, and that is going to be what is that? Spontaneous. So obviously, when can I promptly say, when can I say for sure that T delta S value will be greater than delta H? Only at high temperatures, right? So these are the reactions or processes which will become spontaneous only at higher temperatures, right? When delta S is positive, like see, don't mug up anything, right? This is all just mathematics, right? At what temperature it is going to become spontaneous. Overall, what you have to understand, for us to have a spontaneous process, delta G should be less than 0. As simple as that. Okay, right? Fine. So that is all about this reaction, right? You will see this continuing. You will see about this delta G coming up in the next chapter in year 12. This will be continuously following you. This delta G is very, 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 very important. Okay, so we will speak about, we will connect this with equilibrium. In your 12th class, we'll be connecting with the rate of the chemical reactions. So many things, like we'll be connecting with something called as redox potentials, right? All these things will be able to connect with the help of your delta G. Everything is connected. Delta G is actually connected with almost every other chemical term, or say any other mathematical term we have in chemistry or physics, right? Almost is connected. Okay, so we'll be able to get a lot of insight about delta G, how is it connected, how is it not connected, all those things. Okay, any particular question anybody has? You want to ask me? Okay, right. So that is about this chapter. Thermodynamics is done. Okay, so if you just go through the chapter, if at all I have missed anything, please let me know. Right, that also I'll be able to teach you. Is that fine? Right. So next class will be starting, I think, on tomorrow's class, Sunday's class. We'll be starting with the equilibrium. Okay, and I heard that S and P block elements was taken by some other faculty, right? I heard that S block elements was taken by some other faculty. So he or she, whomever is taking, he or she will be taking your P block also. Okay, so I will be completing your equilibrium chapter, right? That will take some time, right? Maybe before this month ends, we'll be able to complete your equilibrium chapter also, and we'll take some extra classes wherever possible. Okay, right? So yeah, I am going to stop sharing and we can end the class. Right. Thank you so much. Thank you so much.